Right. So, for the next 20 minutes or so, just rearranging myself a little bit. So for the next 20 minutes or so, I am going to talk about emotions and facial expressions. And then I'm going to hand over to Tim, who is a new PhD student in my lab, who's going to talk to you guys about deep fakes and tell you a little bit about his upcoming PhD project. So first, I wanted to introduce you to my lab group. So this is my lab group, and as you can see, they're very sociable beings, but also we study social cognition. So in my lab, we study all sorts of things about social behavior and social connection. So we look at emotions and facial expressions, and I'm going to talk about that today, but we also look at things like empathy, things like theory of mind, how other people understand what other people are thinking and feeling. And we look at body language. And we work with autistic people, and we also work with people with Parkinson's disease to understand how their social abilities change with the progression of Parkinson's disease. I've been working on this topic now for over 10 years, and I started with some work during my own PhD studies that was about body movements. And what we saw back then and also recently in my lab is that your body movements really help to communicate how you're thinking and feeling on the inside. So many labs around the world have shown this, and this is just an example from our own lab group. But what you see on this graph is that we've got the speed of body movements, which we recorded by asking people to walk up and down something called a gait map that records how they move. And we asked them to try to express anger, happiness, and sadness. And what you can see is that people always move faster when they're expressing these high arousal emotions like anger and happiness, compared to when they're expressing low arousal emotions like sadness. And so what this means is that in this little cartoon, you can easily see that this guy is depicting sadness, right? But it's not just his body posture. It's not just the way that it is kind of hunched over, but it's also the speed of his movements that is telling you about how sad he is. When I set up my own lab in Birmingham, say like 5, 6 years ago, we wanted to extend this, not just looking at body movements, but to also start looking at facial expressions. So we did what all good scientists do, and we went to the literature, and we found that for some reason or another, there really wasn't that much information around at the time about how people move their face when they're expressing different emotions. So we knew from existing studies that had looked at sort of photographs, kind of static images of faces. We knew what people were doing with their face. So we know that when people are depicting sadness, they tend to turn their mouth down and they might look down as well. But we knew nothing about the kind of dynamics or the speed of how that was happening. So in this first set of studies, we went about investigating that. And I mean, we have a very kind of, in this picture, this depicts a very rudimentary setup. It's now looking a little bit more sophisticated in my lab, but at the time we used this polystyrene frame, which I think came from a laptop or some sort of computer that had been delivered to the lab. And we wanted people to stay within this frame so that they would stay in the frame of the video camera that we were using to record their expressions. And we set up this kind of algorithmic pipeline that enabled us to track the movement of 36 different points around the face. And we asked people to please express happiness, anger, and sadness. And we also asked them to say sentences in a happy way, an angry way, and a sad way. So they had to say things like, my name is John, and I'm a scientist. And so if they were saying it in a sad way, they'd be like, my name is John, and I'm a scientist. People really got into this task. It was actually great video footage that we got from this task. And to analyze all of this information, we, in this initial analysis protocol, focused on a number of different kind of face movements or face distances that we knew would probably be key in expressing emotions. What we found when we looked at this data was that the same thing that applied to body movements also applied to faces. So in other words, on these graphs, you can see some mouth movements at the top, and you can also see eyebrow widening movements at the bottom, and you've got speed on the vertical axis. And you can see that people always move their facial features faster when they are depicting high arousal emotions like happiness and anger, and they move their facial features slower when they're depicting sadness. So we knew that speed was something that was communicating people's emotions, that people were changing when they were expressing different emotions. But we didn't know from this original study if people are actually picking up on that. Like when I'm looking at somebody else's face, am I really paying attention to speed, or am I just looking at whether their mouth is going down at the corners? So to test that, we did a second study where we took these animations of faces and we played around with the speed so that some of them were abnormally fast and some of them were abnormally slow. And then we got people to rate how happy, how angry, and how sad is the person feeling in the animation. And we found that it was indeed the case that manipulating speed, playing around with it, really affected people's judgments. So in other words, what we found was that if you took an angry facial expression, it still has all the characteristics of anger, but you slow it down, people start to see it as looking sad. And if you take a sad facial expression that still has the downturned mouth and everything, and you speed it up, it starts to look angry. So speed is actually a really important cue that helps us to figure out how other people are feeling. So we were pretty happy with this kind of these initial explorations, these initial studies that we'd done in this field, and we felt like we've added something to the literature. This is very interesting, but we also knew at the same time that really we'd kind of oversimplified this a bit because the face is very complex, and we have this very complex musculature. It's probably not the case that when you're angry, you just speed up every single movement on your face. And when you're sad, you just slow down all the movements. It's probably not that your muscles work together in that kind of like coherent way. It's probably more of a complex picture where there are subtly changing dynamics across different parts of the face. So in other words, what we realize is the face is super complex, and we've just really simplified this problem. So in the next study that we did, we took these same videos that we had, and I mean, already they're somewhat simplified, right? Because we've only recorded 36 points on the face. And the studies that we're doing nowadays in the lab, like this week, we're using different recording equipment that enables us to record hundreds of points across the face. But at this point, it was quite good to just focus on these 36 and at least reduce the dimension a little bit. But we took these videos, and these videos, they've still got a lot of information in them because you've got 36 points on the face. We're recording at 60 times a second, and the videos are sometimes, say, 30 seconds. Some of them are a minute long. So that's a lot of data. That's a lot of different face movements that are all happening. And we want to understand, like, is there a way that we can identify patterns in all of that data, in all of those face movements that are telling us when somebody is happy, when they are angry, and when they are sad? So in other words, what we wanted to do was to learn the spatiotemporal structure of all these complex movements. And to do that, we actually used some data reduction methods that are typically used in things like photography. So this is used if, say you took a picture of a panda, say you were lucky enough to be in this position that you could see a panda so closely, and you took a picture of this panda using a really amazing camera, and that camera takes a picture in really high resolution. So you've got thousands of pixels, but you want to store it on your computer in a low dimensional space so that it doesn't take up too much space on your hard disk. What you can do is to identify that in that picture, there's actually some very common patterns. There's lots of pixels that basically tell you all the same information. So for example, in the white fur of the panda, I bet there's loads of pixels that are exactly the same And you can delete all of those pixels that are telling you the same information, and you can end up with a lower resolution version of that image that still, to your brain, to your human eye, looks the same. Maybe not if you were a bumblebee or something, but to the human eye, it still looks the same. And that's because within that image, you've identified these common patterns of pixels that all vary together. So we used those methods to identify common patterns of movement that happen together on the face. And we found that there were common patterns, which was, not a given. And in fact, there were 3 things that we tend to do with our face when we're communicating happiness, sadness, and anger. And these 3 things are like this. So pattern 1 comprises eyelid tightening movements and eyebrow lowering movements. So it's something to do with kind of this like looking down and like slightly frowning. Pattern 2 is about mouth movements, cheek movements, and eye movements. And it's generally characterized by this kind of raising the corners of the lips, crumpling your cheeks up a bit, and crumpling your eyes up a little bit. So it's a kind of smiling movement. And pattern 3 is about brow movements, dropping of the jaw and turning the mouth down. So this is a kind of like frown with like some activity around the mouth, like the mouth going down. Now, when we're expressing different emotions, we're kind of doing all of these things, but just in different proportions and at different times. So let me unpack these images a little bit more for you. So for anger, what we're doing is mainly moving our eyebrows, mainly lowering our eyebrows and closing our eyes a little bit, but also a little bit, more or less the same time, we're doing a kind of, it's kind of like a tight smile. And so what we've found with this analysis is exactly what you might think we would find, that anger is characterized by this kind of frown in the forehead and a bit of a tight downturned smile. For happiness, what we're doing in general is mainly a smile that reaches up into the cheeks and up into the eyes. And around the same time, we're slightly raising the eyebrows. And then for sadness, what we're doing is a downturned smile and some frowning action, followed by lowering of the brows and lowering of the eyelids. And so you can imagine that this characterizes how we think of as sadness, with the mouth going down and the eyelids and eyebrows kind of turning down. So what's really nice about this analysis is that it is confirmed by our real experience. Like, probably there's nothing that I've said here that you think, well, that doesn't sound right. Like, I don't think that anger should look like that on a face. But you might also be thinking, well, that's all very well, but didn't we kind of know all of that information? And yeah, in a way that's true. Like, qualitatively, the information that we've got, it doesn't really tell us anything that new about how expressions happen. But what's really cool about this is that now we've got numbers and we've got statistics on how people in general do facial expressions. And so this might be really useful, and Tim is going to talk a little bit more about this, for detecting when things aren't quite right. So deep fakes are videos of people's movements, their speech, their facial expressions, sometimes their emotional expressions, where somebody has played around with that video and they've changed the dynamics of it. And now, because we've got numbers and statistics about what people normally do with their face, and also about what parts of the face tend to move together and what parts of the face don't tend to move together, we're better able to figure out when something is not quite as it should be. So this might be really useful for things like authenticity judgments. It might also be really useful for things like social robots, because we can use the numbers, we can use the data that we have to help to animate these robot faces, um, constraining them so that they don't do weird expressions like this, where parts of the face that aren't meant to move together are moving together. And we know now what parts of the face should be moving together so we can better animate these social robots. And another application that my lab is looking into relates to developmental conditions and many other conditions, in fact. So one of the studies that we're working on at the moment is to try to characterize expressions of happiness, anger, and sadness in autistic and non-autistic populations. And so I will show you some preliminary results that we have from this. When I play these videos, you're going to look at them and think, well, you've just played me the same thing twice because they look almost identical. And that's what's really interesting about this, that to the naked eye, these expressions do look really similar. But with our algorithms, we're able to detect some small differences. So let me see if I can actually play them. So these videos are the average, like taking an average over 25 autistic people, that's what you're seeing on the left-hand side, and 25 non-autistic people on the right-hand side. And that is the average expression for the group. So it's not anybody's real expression, but it's generally what these different groups tend to do with their face when they're expressing happiness. And you can hardly see a difference there, but when we apply some of our algorithms, then we see, is this going to work? That there are slight differences in activity in the forehead region. And what we are showing there is that non-autistic individuals, when they're expressing happiness, tend to be using their forehead a little bit more to communicate that information, and also a little bit more activity around the corners of their mouth compared to non-autistic adults. We found similar results as well for anger and sadness. So we found that for anger, again, non-autistic people were really using the forehead region to communicate that information. Whereas for sadness, it was actually the autistic adults that were using the forehead region a bit more, and non-autistic individuals were more kind of in the jaw region. So what we're seeing here is that there are these kind of subtle differences in expressions between autistic and non-autistic individuals. And what that's helping us to do at the moment is to work with a company to develop some algorithms which might help us with autism diagnosis in children. So we'll see how that goes, and fingers crossed for that. And also, this is really helping us to understand that I think a lot of the time autistic individuals get blamed for not understanding other people's facial expressions, whereas actually in some of the other work we've been doing, we've been finding that non-autistic people often don't understand the facial expressions of autistic people. So it's helping us to change the narrative around that a little bit. So that's what I have to say about emotion and facial expressions. We'll come to a question and answer session later on, but first I want to pass over to Tim, who's going to tell you a little bit more about deepfakes.
Thank you, Jen. Okay, let me just share my screen quickly. Okay. So I just wanted to talk a little bit about what my PhD project will be on. I have only just started, so I haven't actually done any research yet, but I have quite a few ideas. So I will start by talking a little bit about deepfakes, what they are, how they are used in everyday applications, why they are a problem, how they're created, and then I will talk a little bit at the end about what my research will be about. So, a common definition of deepfakes is that they are synthetic media, images, video, audio, generated by artificial intelligence to portray something that does not actually exist in reality or something that has never occurred before. The word deepfake itself actually combines the two deepfake and fake, deep learning and fake. deep learning refers to a subset of artificial intelligence that's used to create them. This term has been around since 2017. It originated on Reddit when people were sharing photos of celebrity face swaps. So there are different types of deepfakes as well. The common one is face swapping, also facial reenactment. So face swapping is when you put someone else's face on a different body, a different head. And facial reenactment is when you take, for example, a photo of a famous celebrity and you reenact their facial movements to look like they're doing something that they haven't done before. So this image here, actually, I was going to sort of ask anyone if they could guess which row is real and which row is fake. But I'll just tell you now that the bottom row are the deep fakes and the top row are the real photos. Okay, so if we look at a very brief timeline of the evolution of deepfakes, we can see that very early deepfake technology actually originated in 1997 with the video rewrite program. And this could automatically modify videos of a person speaking to make it seem like they are saying something from a different audio track. Fast forward to 2014, generative adversarial networks came onto the scene, which are the main technology behind deepfakes, and I will talk about this in a bit. But it wasn't until 2017 when the term deepfake actually emerged. By 2019, deepfakes had started to take off and they were being used in a variety of smartphone applications like Face Swap. I've got an example here of the Chinese app called Zao. And while these are relatively harmless applications, there's been quite a few malicious applications like Deep Nude, which, as the name suggests, are a massive problem and need to be addressed. And these have also contributed to a lot of non-consensual pornography, which is one of the biggest issues with deepfakes right now. In 2020, deepfakes were becoming a lot more popular in the media. The example I have here is of a documentary about the persecution of gay people in Russia, where they had genuine footage of victims that they wanted to show in the documentary, but they didn't want to reveal the identities of these people. So their solution was to hire actors who looked similar and then use deepfake technology to put their faces on the victims, thereby protecting their identities. So now, fast forward to 2024, we are at a point where deepfake technology has massively improved from these examples you can see. It's become a lot more widespread and is being used a lot for misinformation. Why is it not going? There we go. So here are some examples of deepfakes being used in some everyday applications. We've got Snapchat here. We've got another application that does a similar thing. Some examples you might be aware of, David Beckham's malaria awareness campaign in 2019 depicted him speaking 9 different languages using deepfake audio and lip syncing technology. Another example, James Earl Jones, who sadly passed away recently, he gave his permission for Disney to use deepfake technology to recreate his iconic Darth Vader voice for future projects. There was also an example last year of a seemingly real song featuring Drake and The Weeknd, 2 popular artists, which actually turned out to be fake using deepfake audio technology. And this fooled a lot of people. And I've also put an example in the bottom right here from a French advert for the Women's World Cup. And for this, they created deepfakes from footage of the women's football team to make it seem like it was the men's team playing. This also fooled a lot of people. So I just want to talk briefly about the darker side of deepfakes, which is the main reason why there's such a pressing need for research in this area. A report in 2019 estimated that 96% of all deepfakes were pornographic. And of all these deepfakes, it's estimated that they are mainly all non-consensual, which is a massive issue. And this is perhaps the most biggest issue with deepfakes currently. This has been reflected recently when the UK amended the Criminal Justice Bill to criminalise the creation and distribution of non-consensual deepfake pornography. This still remains a big issue, though. Quite recently, there's been a deepfake pornography scandal in South Korean high schools, which gained a lot of attention in the media. Deepfakes have also been used for political misinformation this year, especially. There's been two notable examples from this year where deepfake audio was created of the Mayor of London and Joe Biden, and this was used to mislead the public. The recent Hollywood actors strike as well is a good example, where studios wanted to create deepfakes of their actors to save money from hiring them. Luckily, this was prevented, and also misinformation in general. There's been an example in the news recently of someone creating a deepfake of someone and then using it to call their loved ones and ask them to send them money, basically. And this worked. But I also want to mention that there are some genuine use cases of deepfakes. Not all of them are bad. So they can use it for animation and content creation. This example in the bottom left shows an actor, and although he's wearing a lot of motion capture technology, they are still using deepfake technology nonetheless to recreate his face and his facial expressions to a very high degree. Deepfakes can also be used to create digital assistants that can seem genuine and lifelike. This could be used to make interactions on the internet with chatbots, for example, a much better experience. This example on the right shows how deepfakes can be used in education. In this example, they've used a deepfake of Abraham Lincoln, seemingly bringing him to life. And there are some applications of this to educational settings. For example, a deepfake of Abraham Lincoln could give a brief history class to children at school, which would make it a bit more entertaining. So now I want to talk briefly about how deepfakes are created. The main technology behind deepfakes are generative adversarial networks, or GANs for short. So the GAN consists of two main components, the generator and the discriminator. The generator's job is to take random noise and attempt to recreate images from the training data. The training data, by the way, consists of real photos of real people. The discriminator's job is to grade the generator's attempts based on how real or close they are to the real images. And over time, the generator will learn from the feedback from the discriminator, and it will gradually improve and improve until it actually fools the discriminator into thinking that the images they create are real. And when this happens, we get the example on the right, which all look like real people, but they are actually completely fake. A good analogy for this is like a teacher and a student. The student is producing homework, which is marked by the teacher. The student starts off really poorly because they haven't been taught yet, but over time, the teacher grades their work and tells them how to improve. And eventually, the student will pass or even get 100% on their homework. The accuracy measure for this is loss, which measures the difference between the training data image and the image that is produced. Over time, the generator will build up a map of relationships between the features it has extracted from the training data images. These features can include things like eyes, nose, mouth, hair, etc. But it can also include features like young, old, male, female, emotional expressions, for example. And this map of feature relationships is called the latent space. And the structure of this latent space is very highly organized, where similar features are grouped together. So, for example, eyes and teeth will not be grouped together because they're not similar. But, for example, different eye shapes or different eye colors will be grouped together. If you can find the latent code for a face in this space, which is like the combination of the features to make up a face, you can manipulate this face by moving that latent code to a different region in the latent space. So, for example, in the bottom left, we can see three female faces transforming into male faces. And this is achieved by taking the latent code for these faces and moving it to the corresponding area for the male faces. And this process looks something similar like the example in the bottom right, where it's moving across the latent space. And for this example, they're generating images at each step to make it look like it's morphing into someone else. So how do we detect deepfakes? So far, there are three main methods. The first is to use machine learning techniques to identify any sort of inconsistencies or anomalies in the deepfake that might be invisible to the naked eye. And so far, this is the most popular approach to deepfake detection. Another approach is to examine physiological signals of the deepfake. These are things like eye movement, speech patterns, blinking, for example, to detect anomalies in these behaviors. And I will get into this in a lot more detail in a minute. The other approach is to train and educate people to know more about deepfakes and to understand how to look for them. But this isn't ideal because research has shown that humans often struggle to distinguish between real and fake people, and they often perform no better than chance. And humans are also typically very overconfident in their judgments too, which doesn't help. The main challenge with all of these approaches is that deepfake generation techniques are constantly getting better and better. Existing approaches we have for detecting them are often not robust enough to be generalizable to future and more advanced deepfakes. Also, a lot of machine learning and deep learning approaches are very computationally intensive, which means it requires a lot of power and time to come to a decision on whether something's real or not. And this isn't suitable for detecting deepfakes that are in the wild, so to speak, because it takes too much time. Um, Also, deepfakes that have a very high level of compression, um, which means like if it's very blurry or a grainy video, or any sort of occlusions in the video, like sunglasses, these are a lot harder to detect in machine learning approaches. That being said, there is a very clear need for a deepfake detection approach that is firstly computationally inexpensive. So that means it's cheap and quick to run. Um, that can be applied to real-time detection, that can generalize to wild deepfakes and is robust to future deepfakes that might be more advanced to what we have now. There's also a need for something that is explainable and transparent. So the decision of whether something is real or fake has to be explainable to the person to the user who wants to know. And the process of deciding whether this is real or fake has to be very clear and understandable. And finally, there's a need for an approach that is multimodal. And this means combining visual, audio, and physiological data together. So this leads on to our research, which I will be doing over the next 4 years. So current deepfakes, although they might look realistic, they struggle to accurately replicate specific features and nuances. So if we take a video of a deepfake and we extract a single frame as a still image, it might seem indistinguishable from reality. But when we examine the deepfake over time, as the video continues to play, there are often visual inconsistencies that give it away. So this example I've got here on the screen is taken from my research poster, which I presented on Monday. It's not the best example, but it illustrates the different domains we are interested in. So the still image by itself, we call the spatial domain, which refers to how things look at one specific instance. When we analyze the frames of a video over time, we call this the temporal domain. Together, these domains are called the spatiotemporal domain. And this involves looking at how things are in a specific, or sorry, how things look in a specific individual instance and how they look and change over time as well. And so far, there are a lack of studies that focus on the spatiotemporal domain, and there are very, very few that consider all three of these domains. But the one study we did find found that deepfake detection actually improves when we consider these domains all together. And this is just a figure I took from that paper, and it shows the three different domains for four different deepfake generation techniques. In this paper, they trained three different machine learning models on each domain. The yellow and blue areas on the faces show the areas that the model attended to the most, and this highlights the areas that might have inconsistencies or anomalies. And you can see that each model focused on different areas. So if we combine all this together, there's more data and there's a higher chance that we can detect the deepfake. More recently, there are studies that focus on using human behavioral characteristics to detect deepfakes. For example, there are studies that look for anomalies in eye blinking patterns, the eyebrow region, speech profile, if it's an audio deepfake, facial expressions, heart rates even. So deepfakes typically struggle to accurately replicate these nuances in these behaviors. And we can exploit this weakness to detect them. So the example in the top right shows an example from a study looking at inconsistencies in facial expressions. They found that in the real videos, the change between facial expressions is very subtle. But in the deepfake videos, the change is not very subtle at all. And they use this to detect whether a video is real or not. The example below this, it shows a technique called Eulerian video magnification. And what this does is it basically visualizes the pulse of someone in a video by amplifying the subtle color changes in their skin. And this reveals their blood flow and their pulse. And from this, we can work out their heart rate. And recent studies have successfully used this technique to detect deepfakes, which cannot replicate this yet. So the overarching goal of my research is to create a fingerprint system. And this fingerprint system will take all these different biobehavioral cues and it will look at each of them to detect any anomalies or inconsistencies. This is based on the idea that no two people have the same fingerprint. We also believe that each individual human displays unique and consistent patterns in their behavior, which are only unique to them. So for example, when I'm talking now, the way my lips move, the way my eyes move, my facial expressions are all unique to me and the context I am in. If we can work out this for individual people, we can use this to determine whether a video of them is real or not. And in theory, this approach should be a lot more computationally cheaper compared to previous techniques. It should also be robust to future deepfake technology, at least for now. There's also a very real chance that deepfakes in the future will be able to replicate this to a believable degree, but we don't believe this is going to happen anytime soon. This approach will also be explainable. So for example, if we detect a video as a deepfake, we can explain why we came to that decision. For example, it could be inconsistent eye movements while the person is speaking. And this is also multimodal because it combines visual, audio, and physiological data. So I just want to talk now briefly about the first study that I will be doing. So for this, we're going to focus on spatiotemporal inconsistencies in facial movements. And we are going to get participants to watch videos of real and fake videos, and we're going to get them to judge whether it's real or fake. We will also be measuring their physiological reactions using electrodes while they watch the videos. So these are the research questions for this study. For the methodology, it will be a within subjects design. So all participants will be subject to all the conditions. We've got 3 conditions, which I'll speak about after this. And we are going to be using the Google Jigsaw dataset, which is a subset in the face forensics dataset. The face forensics dataset is one of the most common dataset that contains deepfakes for research. And the Google Jigsaw part of it uses paid actors to create deepfakes. So the first condition is the full stimuli condition. In this one, participants will view both real and fake deepfake videos, and this will have all the information available to them. So they can see the background, the lighting, the body movement, the body language, and this allows authenticity judgments to be based on the full range of perceptual cues, so all the information is available to them. The next condition is the point light display condition. So for this, we have removed all background and color information from the previous full stimuli, and this leaves us with only the facial structure in the form of little dots on the screen. And these examples you can see here are actually from this example. The reason for doing this is that it isolates the pure spatiotemporal structure of the face, and participants cannot judge whether it's real or fake based on any other external information, such as body language, background, or lighting, for example. The third condition is emotional expressions. So the full stimuli we have can be split into happy, angry, disgust, and neutral emotion. And in this condition, we want to see if spatial temporal inconsistencies are more perceptible in high arousal emotions like anger, or in expressions that require more complex facial dynamics, for example. So we will be collecting a variety of data for this. Firstly, we will be collecting gaze data of the participant through eye tracking. And these two pictures at the top show the placement for our eye tracker and the software we're going to use to track this. For physiological data, we will be using shimmer devices, which have electrodes on them, and we can use these to measure things like respiration, skin conductance, ECG, heart rate, for example. And these two pictures at the bottom show how the shimmer devices will be set up on the participant to collect their physiological responses. So our analysis for this can be split into two main parts. The first part will be a stimuli-based analysis, where we will be analyzing the video stimuli to detect spatiotemporal inconsistencies. To do this, we will extract and model the spatiotemporal structures from the video frames to examine how facial movements change over time. We will then apply dimensionality reduction, which Jen talked about earlier, and we will then train machine learning classifiers on the reduced feature set, to detect deepfake videos. And the outcome of this that we would like is to have a model that is capable of detecting deepfakes by learning patterns of inconsistency in facial movements. I just wanted to include this quickly as well. We've actually already started this part of the analysis, and this figure here has just been generated from the video stimuli. So we extracted action unit data from the deepfake videos, and action units are basically individual muscles in your face that move when you make an expression. For example, one action unit would be when you raise your eyebrows, it activates the muscles in your face, and we can capture this. So this figure shows the intensity of all these action units from one specific video we showed to the participant. For example, we can see that the action unit for the inner brow raiser on the very far left of the graph is mostly unactivated because it's blue until halfway through the video when it becomes red, and this is when it's activated. So this basically shows how facial expressions are changing over the video, which one's activated, which ones aren't. This figure here is for a real video, not a deepfake one, but this one is for a deepfake video, and you can see it looks a bit different, where some action units are constantly activated at full intensity, but others are barely activated at all. So we want to use this and compare them to see if there are any differences between deepfake and real videos. The final part of our analysis is observer-based analysis. So this includes how the participants will respond to the stimuli when they watch them. And to do this, we will analyze the physiological data that we collect, and we will correlate it with any spatiotemporal inconsistencies in the videos that they watched. And from this, we want to identify specific visual cues or any facial landmarks that capture the participant's attention or arouses suspicion in them. And from this, we want to build predictive models that can use this data to link biobehavioral patterns with participants' likelihood of judging a video as fake. And the overall outcome of this we would like is to have insights into the subconscious and conscious cues that participants use to identify deepfakes. It's also worth mentioning that my research over the next 4 years will be in collaboration with the National Police Chief Council, and they basically bring together all the police leaders in the country, and they address prominent issues that society are facing, such as deepfakes, for example. And I haven't begun work with them yet, but I expect we will be testing any sort of research we do on real world use cases, and I'll be working with them to gain better insights into the issue of deepfakes. And finally, I just want to mention some of the challenges surrounding this area of research. The main one is that deepfake generation techniques are constantly improving. We are at a point now where deepfakes are nearly indistinguishable from reality. So we constantly need to find new ways to combat this. Research into deepfake detection is quickly becoming out of date. A lot of deepfake research over the past couple of years will soon be very redundant, if not already. And there's a very, very real possibility that the research we're doing now will be redundant in the future too, if deepfakes can find a way to replicate these behaviors. So it's basically a constant cat and mouse game. We also must be very selective and careful in what we publish, because our work can inform the generation of even better deepfakes. So, for example, if we highlight and exploit a fundamental flaw in deepfakes and we publish this, it's basically telling the deepfake creators how to improve for the next time. Um, and the reality is that in the future, we will have to combine as many deepfake detection methods as we can with other approaches like watermarking or blockchain technologies to determine authenticity. So yeah, thank you for your attention.